Jupiter is the giant of the solar system, the fifth planet from the Sun, and by a wide margin the largest. Its mass is some 318 times that of the Earth, and more than 2.5 times the mass of all the other planets put together. If you could gather every other world, every moon, asteroid and comet into a single ball, Jupiter would still outweigh them all. And yet, for all that mass, it is a curiously insubstantial thing. Its average density is barely greater than that of water, and far below the Earth's, because Jupiter is made overwhelmingly of the two lightest elements in the universe, hydrogen and helium, squeezed and piled deep, but never gathered into the dense rock and iron that build a world like ours. It is not a scaled-up Earth. It is a different kind of object altogether, a vast, fluid ball of gas and liquid, with no solid ground anywhere upon it, held together and lit from within by nothing more than its own colossal weight. Jupiter's dimensions match its grandeur. Its radius at the equator is just under 72,000 kilometres, about 11 times the Earth's, and more than 1,300 Earths would fit inside the volume it encloses. But the most telling number is not its size, it is its speed. Jupiter turns on its axis once every 9 hours and 55 minutes, the shortest day of any planet, so that a point on its equator is travelling at more than 12 kilometres every second purely from the spin. A body that large turning that fast cannot hold a perfect sphere. Being fluid, it bulges. Jupiter is measurably flattened, its equator standing some 4,600 kilometres farther from the centre than its poles, the most pronounced flattening of any planet, plain to see in any good telescope. That squashed figure is a message. It tells us the planet is fluid, that it spins rapidly, and, from the precise degree of the bulge, that its mass is gathered toward the centre rather than spread evenly through the ball. Jupiter circles the Sun at a little over 5 times the Earth's distance, some 778 million kilometres, taking almost 12 years to complete a single orbit. Out there the Sun is a shrunken thing and its warmth is faint. Jupiter receives less than 4% of the sunlight that falls on the Earth. Its axis stands very nearly upright, tilted barely 3 degrees, so that unlike the Earth and Mars it has essentially no seasons. And here lies the first great clue to its inner life. If Jupiter were warmed by sunlight alone, its temperature would settle at around 110 degrees above absolute zero. In fact, it is markedly warmer than that. The planet radiates into space nearly twice as much energy as it receives from the Sun. Something inside Jupiter is still generating heat, a hidden furnace, 4.5 billion years after the planet formed, that will prove central to almost everything else about it. Jupiter's sheer mass gives it a roll out of all proportion even to its size. The common centre about which Jupiter and the Sun both turn lies just outside the Sun's visible surface, so the Sun itself traces a small wobble as the great planet swings around it, the very motion astronomers now watch for in distant stars to betray unseen planets of their own. Nearer at hand, Jupiter rules the asteroid belt, its gravity carving empty lanes through it, and marshalling 2 great swarms of asteroids that ride along its own orbit, ahead of and behind it. It is sometimes called the shield of the inner solar system, deflecting comets that might otherwise strike the Earth, a picture now known to be only half true, for Jupiter both removes and occasionally redirects them, but its power was displayed beyond doubt in 1994, when the comet Shoemaker Levy IX, torn into a string of fragments by Jovian tides, plunged into the planet piece after piece, the first collision between 2 worlds that humanity ever watched as it happened. Jupiter has no surface. What we see when we look at it is the top of an atmosphere thousands of kilometres deep, grading imperceptibly downward into the fluid interior with no boundary a spacecraft could ever land upon. That atmosphere is banded, wrapped in alternating, light and dark stripes running parallel to the equator, the most familiar face of the planet. The pale bands, called zones, are regions of rising gas, cooler and higher, capped with bright clouds of ammonia ice. The darker bands, the belts, are regions of sinking gas where the upper cloud is cleared away to reveal warmer, deeper material below. Between them run powerful winds, jet streams blowing east and west, alternating in direction from one band to the next, reaching speeds of well over 100 meters per second, and holding their latitudes steady for decade after decade. The tans and browns and famous reds of the bands are not the colors of the clouds themselves, which would be white. They come from small quantities of some other compound, tinting the cloud tops, whose exact chemistry remains, remarkably, still unknown. By its makeup, the atmosphere is close to the Sun's, about 9 parts hydrogen to 1 part helium, with a trace, a fraction of 1% of methane, ammonia and water that nonetheless drives most of the visible weather. Where these vapors rise and cool to freezing, they condense into distinct decks of cloud, one above another, sorted by the temperature at which each freezes. An upper deck of ammonia ice, a middle deck of an ammonia-sulfur compound, and deepest of the three, a layer of ordinary water cloud, tens of kilometers down, where the pressure is several times that at the Earth's surface. Much of what we know of this came from a single probe. In 1995, the Galileo spacecraft dropped an instrumented capsule into Jupiter, which radioed its readings back as it fell until the mounting heat and pressure destroyed it. But it chanced to fall into an unusually dry, cloudless patch, a Jovian desert, and so measured far less water than the planet holds on average, leaving the true abundance an open question for decades. That same Galileo probe carried a subtler puzzle back with it. It found that helium in Jupiter's outer air is depleted. There is measurably less of it than the gas from which the planet formed should have contained, and that the rare gas neon is depleted, far more sharply still, stripped to about a tenth of its expected abundance. The explanation is one of the most elegant inferences in all of planetary science. Deep inside Jupiter, at pressures of 1,000,000 or more times the Earth's atmosphere and temperatures of many thousands of degrees, helium ceases to mix freely with the hydrogen around it. It condenses instead into fine droplets. Being heavier, those droplets rain downward, falling toward the planet's center and carrying dissolved neon with them, for neon dissolves readily in liquid helium. Helium rain, as it is called thus, drains both gases from the upper layers at a single stroke, explaining the twin shortfalls exactly. And as those droplets fall, they release gravitational energy as heat, which is very probably the hidden furnace that keeps Jupiter glowing warmer than the sun alone could ever make it. It is tempting, faced with a warm ball of hydrogen radiating its own heat, to think of Jupiter as a star that failed to catch light, and there is a grain of truth in the comparison, but only a grain. Jupiter's inner warmth comes not from nuclear fire but from slow gravitational settling. The planet is very gradually shrinking, contracting perhaps a millimeter a year, and the energy released as it does so, together with the helium rain, supplies its gentle glow. It is the same process once wrongly proposed to power the sun itself before nuclear fusion was understood, but Jupiter falls far short of stardom. To fuse even deuterium, the easiest of nuclear fuels, a body must be some 13 times Jupiter's mass. To burn ordinary hydrogen as a true star does around 80 times. Jupiter has but 1/1000th of the sun's mass. It is, and always was, a planet kept warm not by the fire of fusion, but only by the slow surrender of its own weight. To descend into Jupiter, as no craft ever could, would be to pass through a single vast ocean of hydrogen, changing its character with depth, rather than through any sequence of solid floors. For the first tenth or so of the way down, the hydrogen is the ordinary molecular gas grading into liquid, an insulating fluid churning with convection. But some 15 to 20,000 kilometers down, where the pressure passes 1,000,000 times that at the Earth's surface and the temperature climbs into the thousands of degrees, hydrogen undergoes an extraordinary change. It turns into a metal. Its molecules are torn apart, its electrons set free to roam, and the fluid becomes an excellent conductor of electricity, liquid metallic hydrogen, a substance we can barely make for a flicker oven, instant in the most violent laboratory experiments on Earth, but which makes up the bulk of this planet. Deeper still, the temperature reaches perhaps 20,000 degrees and the pressure tens of millions of atmospheres, in a hot, dense metallic sea enclosing the planet's very heart. For all that we could deduce of this hidden interior, most of it remained inference until a single spacecraft went to test it. NASA Juno probe, launched in 2011, slipped into orbit around Jupiter on the 4th of July, 2016, and set about probing beneath the clouds. It flies a long, looping, egg-shaped orbit that carries it, once every couple of months, skimming just a few thousand kilometers above the cloud tops before swinging far out again, a path carefully threaded to dive beneath the planet's most dangerous radiation and spend most of its time clear of it. Even so, its most delicate electronics ride inside a vault of titanium, 180 kilograms of metal armor against a radiation storm fierce enough to kill an unshielded craft. Spinning, solar-powered, the most distant solar-powered spacecraft ever flown, Juno carries instruments to weigh the planet's gravity with exquisite precision, to sound its deep atmosphere at microwave wavelengths, and to map its magnetic field, and almost at once it began overturning what we thought we knew. the greatest of Juno's surprises came from gravity. By tracking how the probe's radio signal was minutely quickened and slowed as the planet's uneven pull tugged upon it, scientists mapped the distribution of mass inside Jupiter as never before, and found the textbook picture wrong. For decades, models had assumed a compact core, a dense ball of rock and ice perhaps 10 or 20 times the Earth's mass, about which the gas had gathered as the planet formed. Juno's measurements could not be squared with any such thing. What they favor, instead, is a dilute core, a region where the heavy elements are not gathered into a sharp central ball at all, but smeared outward, mixed into the metallic hydrogen through perhaps half the planet's radius. The clean old line between core and envelope simply dissolves. Whether Jupiter's core was never compact, or was stirred up and blurred over the ages, or churned by some giant impact early in its history, is now an open and much debated question, and among the liveliest in the study of how giant planets are built. That churning sea of metallic hydrogen does more than store heat. It generates the strongest magnetic field of any planet in the solar system. As the electrically conducting fluid convects, organized by the planet's rapid spin, it sustains vast electric currents that maintain the field, a dynamo of the same essential kind that works inside the Earth, but on a titanic scale. At Jupiter's cloud tops, the field is some 14 times stronger than the Earth's at its surface, and the planet's overall magnetic strength thousands of times greater. Juno, passing closer to the planet than any craft before it, found that field to be far stranger than a simple bar magnet tilt. Its lines emerge from the northern hemisphere in a narrow, intense band, while in the south a single concentrated patch near the equator, nicknamed the Great Blue Spot, dominates. And by comparing Juno's readings with those of spacecraft that had passed decades earlier, scientists caught the field slowly changing over time. The first time such drift has ever been measured for any planet but our own. The field carves out a colossal bubble in space around the planet, the magnetosphere, the largest structure in the solar system save the Sun's own domain. On the side facing the Sun, it holds the solar wind off at 60 to 90 times the radius of Jupiter itself. Downwind it streams into a vast tail reaching beyond the orbit of Saturn. Were this bubble visible from the Earth, it would loom larger in our sky than the full moon. And unlike the Earth's, which is driven mainly by the solar wind, Jupiter's magnetosphere is powered from within, filled by its innermost great moon, the volcanic Io, which feeds a ton of gas into the surrounding space every second. Flung outward by the planet's spin, this material forms a disk of electrified gas whose currents, where they finally fail to keep pace with the turning planet, pour energy down into the atmosphere at the poles. There they light the most powerful aurorae in the solar system, glowing in visible light, in ultraviolet and uniquely in X-rays, and, unlike the Earth's blazing whether or not the Sun is stormy, for they are lit from within, no feature of Jupiter is more famous than the Great Red Spot, a single storm larger than the Earth that has raged in the planet's southern skies for centuries. It is an anticyclone, a great, high-pressure whirlpool of cloud, rolling between two opposing jet streams like a ball caught between two moving belts. It has been watched continuously through telescopes since at least 1830, and possibly, if certain 17th century reports describe the same spot for far longer still, a storm that has outlasted by a factor of hundreds anything the Earth has ever known. To sit in one place and turn for centuries is a feat no terrestrial hurricane, breaking itself apart within days, could ever approach. And how the Great Red Spot manages it is a question that has occupied astronomers for as long as they have been able to see it. And yet the Great Red Spot is not eternal, and it is changing before our eyes. Over the past century and a half it has steadily shrunk. Once wide enough to swallow 3 Earths side by side, it now spans little more than one its width, less than half what 19th century observers recorded. As it narrows, curiously, it has grown taller and its winds have quickened, now racing round its edge at over 400 kilometres an hour. Why it shrinks, no one is sure. One recent study suggests it is being starved, as fewer of the smaller storms that once merged into it now feed it. Its survival across the centuries owes much to its position, penned between 2 jets that blow in opposite directions and continually resupply its spin, and to its habit of swallowing lesser storms whole. Its red colour, like the bands, comes from some compound still unidentified, perhaps material dredged up and altered by sunlight, for a neighbouring storm that reddened within living memory shows these vortices can take on their colour in just a few years. Juno turned the Great Red Spot from a pattern on the clouds into a structure with depth. Passing overhead, its microwave instrument peered beneath the visible swirl, and found the storm's warm, organized circulation reaching far down, at least 200 or 300 kilometers below the cloud tops, 50 to 100 times deeper than the Earth's oceans. A separate reading, drawn from the storm's faint tug on the spacecraft's motion, set an outer limit of around 500 kilometers. The Great Red Spot, in other words, is not a shallow cap of cloud, but a deep column reaching down into the planet, its base warmer than its top, a structure that helps drive its ferocious winds. It is the same lesson Juno taught again and again. On Jupiter, the weather is not a thin skin over a placid interior, but reaches surprisingly far into the depths, binding the visible face of the planet to the vast convecting fluid beneath. When Juno first swung over Jupiter's poles, it revealed a sight no earlier spacecraft had ever seen, for all had flown above the equator. The poles are not blank, nor do they hold the single great hexagon that frames the north of Saturn. Instead, each is crowned with a geometric cluster of cyclones, arranged with startling regularity. At the North Pole, 8 great storms encircle a ninth at the very center, in a neat octagon. At the south, 5 surround a central sixth, in a pentagon. Each of these cyclones is thousands of kilometers across, with winds of 100 meters per second, and they are locked into their crystalline patterns with a stability that has held, slowly evolving, across years of watching. They are a natural laboratory for the physics of spinning storms, packed together yet neither merging nor flying apart, a balance of forces astronomers are still working to explain. 2 further discoveries completed Juno's remaking of the planet. The first concerned the banded jet streams. By measuring with great delicacy the faint north-south lopsidedness of Jupiter's gravity, scientists showed that those winds are no mere surface pattern, but extend some 3,000 kilometers down into the planet, holding around 1% of its entire mass, before the deep metallic hydrogen breaks them and the interior below turns almost as a solid body. The second settled the old question the dry Galileo probe had left hanging: how much water lies in Jupiter's depths? Sounding the equator at microwave wavelengths, Juno found water there amounting to a few times the Sun's own proportion of oxygen, far more than the desiccated probe had measured, though varying from place to place so that even now the planet's total water remains only partly known. It matters because water carries oxygen, the most abundant of the heavy elements, and its abundance is a fingerprint of where, and from what, Jupiter was born. Jupiter is not merely a planet but a system, attended by at least 95 known moons, and dominated by the 4 great worlds Galileo Galilei first saw through his telescope in 1610, and which still bear the name Galilean. In order outward they are Io, Europa, Ganymede and Callisto, and no 4 bodies in the solar system are more varied. Io is the most volcanically active world known, its surface repaved continually by hundreds of erupting vents, its greatest volcano a lake of lava more than 200 kilometers across. Ganymede is the largest moon in the entire solar system, bigger even than the planet Mercury, and alone among moons generates its own magnetic field. The inner 3 are bound in a beautiful clockwork. For every single orbit Ganymede makes, Europa makes exactly 2 and Io exactly 4, a locked chain of rhythms that keeps their paths slightly elliptical and will not let them settle into perfect circles. That locked rhythm is the engine of the whole system. Because the moons can never quite round out their orbits, each is flexed and kneaded by Jupiter's gravity as its distance rises and falls, and the friction of that endless flexing heats them from within. It is tidal heating that stokes Io's volcanoes, and tidal heating that keeps liquid water, whole oceans of it, from freezing beneath the icy shells of Europa and Ganymede. We know those hidden oceans are there by an elegant trick. As each moon sweeps through Jupiter's tilted magnetic field, the field induces electric currents in any buried layer of salty, conducting water, and those currents betray the ocean by the faint magnetism they in turn give off. Ganymede's ocean may hold more water than all the seas of Earth combined. Only Callisto, the outermost, lies beyond the resonance's grip, cold, quiet and geologically dead, its ancient face the most heavily cratered surface in the solar system, a frozen record of 4 billion years of bombardment. Those buried oceans have made the moons of Jupiter among the most enticing places in the solar system to search for life beyond the Earth, and 2 great missions are now on their way. Europe's JUICE spacecraft, launched in 2023, will reach the Jovian system in the next decade and end its days in orbit around Ganymede, the first craft ever to circle a moon other than our own. NASA Europa Clipper, launched in 2024, will make repeated close passes of Europa to weigh its fitness for life, darting in and out to dodge the killing radiation. Together they carry forward a story Galileo began with a crude glass tube 4 centuries ago, and that Juno has lately rewritten from top to bottom, the story of a planet that is a solar system in miniature. A failed star that never lit, a fluid world with no ground to stand upon, wrapped in the strongest magnetism and the mightiest storm we know, and holding in the dark oceans of its frozen moons one of our best hopes of learning that we are not alone.